Okay, so I will do the so pre-horospherical RPN is just so if it has a pre-horrible as a PN neighborhood, and the lens shaped is, and you have a lens cone as a PN neighborhood here. Okay, so I will skip these details, and so so N neighborhood is a range shape. It has a range shape R and neighborhood or TN neighborhood. So PN neighborhood is range shape is range shape PN neighborhood or TPN neighborhood here. Okay, so real projective orbifold with radial total geodesic end is a strongly tame orbifold with real projective structure. So each end is a R and a T end with a and structure given for each, and n is lens shaped or pre-horospherical if it has a it is a lens shaped or pre-horospherical Rn or lens shaped Tn. Okay. So also we can define Pn bodices, and so Pn bodice is for an R and is a ideal point of the leaves of U1. So if you take the neighborhood like this, and so you can identify with this image on the depth when depth is fixed. Okay, and I should say it's embedding when it's embedding at the ejective. And the set of arrays from BE is so you can denote it by BE, and diplemorphic to n minus one sphere, and this acts as a projective orthomorphism. And you can define the set of rays, space of directions of rays like this, and you take the quotient to be the n over. Okay, so that's the PN neighborhood here. So the cusp case is easy to understand. So in this case, you look at ellipsoid in RPN. And so this is a projection of some null cone of non-degenerate symmetric bilinear form of signature 1n. And the ellipsoid ball is a cross-contractible domain inside, bounded by this ellipsoid containing an an. And so then some this PON1 acts on this B. Then so if you take the discrete group, so acting on this, so if you have some discrete group acting on this is called the whole orbifold, and so cusp is, so this is called the cusp group is a parabolic subgroup, some isomorphic copy in here, and cusp group is a unipotent. Cusp group it is unipotent as well. So that means it doesn't have some elliptic element. That's all that it is. And here I'm just considering when you have some group G containing this discrete subgroup of this gamma tilde E, and then this is compact, then you can actually make this G act on the P and N vertex, and contains this G invariant PN neighborhood actually. So you can so if you have some cases when there's some way to find this group, connected D group, so that this is compact, then you can always do this. So the reason is, of course, you can always find some compact fundamental domain, and you can then use this. So you can actually instead of this taking in complete intersection, you can only look at these things on F. Okay, that's the basic proof of these. And also, I discussed something about unit no eigenvalue actions on the end. I will not discuss it too much here. So the main point is that if you have such, then you can show that these are actually cusp. Okay, cusp group. Okay, that's what I was doing here. And so for examples, you can take something like a hyperbolic finite volume hyperbolic anorbifold with length n minus one whole speaker and maybe totally geodesic boundary. So then so if you remove the boundary component, then these will be the examples what I will be talking about. And so another example is you take n orbifold is some 2 orbifold based on sphere with 3 singularities order 3. And so you take so sphere with 3 singularities, which are order 3. Then these will occur in some examples by Porty and Tillman and so on. Okay. Maybe I didn't explain that too well here. So skip this anyway. So let me explain this here. So you have some interior ellipsoid here, and then what is a group of projective automorphisms. So B has a Hilbert metric, which is a hyperbolic metric times some constant. And so suppose we have some totally geodesic embedded surfaces homotopic to the end. Maybe I should say this is hypersurfaces actually, right? And then these are the boundary components of M. Okay, and then so you remove these. So the outside of this to make a totally geodesic boundary. And then we have these disjoint union of totally geodesic domains, and this group acts on this. And then there is some group acting on this to make it a crossover port. And so suppose that these fixes some common point outside M tilde, then you can form a cone. And then these portion, you can identify these cone with these rest of manifold to obtain R manifold with Rn's. Okay. So you some cut off these and then you make a cone manifold and then you glue these. Okay. So these are called hyper-ideal extension of convex Euro-projective. So when M is hyperbolic, this will be lens by some proposition to come out later here. And so if the N is generated by some homotopy class of finite order or is simple or satisfies a unit middle eigenvalue condition. So unit middle eigenvalue condition means that the polynomial will fix these added products with the value eigenvalue 1. Okay, and then the E has a invariant n-1 dimensional totally geodesic convex domain in the Pn neighborhood, not containing the Pn neighborhood in the closure. Then this is always going to be lens shaped. And right. So the basic idea here is that so this condition will imply that it satisfies the unit middle eigenvalue condition here. And, so the basic reason is if you cut off this totally geodesic domain, then you can put it into an affine put it as an affine cone. and then these unit eigenvalue condition will mean that this group will be SL and R, and then you can find the Kosovo-Limburg function. Okay, I should say these are our special affine group in this case. So therefore, the Kosovo-Limburg function exists, and then you can do the reflection to get the other side, and then you obtain the lens. Okay, so that's so specific example is these two orbifolds with BA sphere with three cone points over the three. So these are generated by elliptic elements. So therefore, it satisfies this unit eigenvalue condition. So in the strongly tame convex real projective three orbifold with RNs whose endpoint is. So you find some examples with the sphere n orbifold is different to the sphere or disk with three shivered edge and three corner reflectors over the three. Then if this is strongly reducible, then it's always lens shaped or is horospherical. Okay, so in this case, you always get a lens shaped or horospherical. So in S33 case, so then the projective actually the final index group is actually G2. So if sigma E is convex, then the convex torus covers this, and then this is just a complete affine plane or convex triangle or half space. So this is obtained by some classification of these such things by Nagano and Yagi. And so because there's order three automorphism, this half space case doesn't happen. So we have only these two cases. So if it's complete affine, then so if this sigma one, then you can use this theorem much later that this is just nilpotent or is a horospherical cusp. Otherwise, you have properly convex tetrahedron, and you can show that there's a total geodesic plane destroying from some vertex, and then you can show that these are actually the things that I talked about with the unit eigenvalue condition, so therefore it's a lens. And then another set of examples are the bending. So we can consider something like hyperbolic manifold with hyperideal ends with a total geodesic n, and then we can take some closed geodesic in it. So these are our three manifolds here. Did I say three manifolds? I should say it's three manifolds. So, and then the right. And then so you take some hyperbolic manifold with hyperbolic ideal n e, and then you can insert support each annuli. So you take some closed geodesic, and then you take 0 times 1, and then you complete it by adding along the radial foliation, and then you can cut this off and then reglue by this sort of the non-diagonalizable elements, which commutes with every. So this will fix the fixed point, and then you'll commit with the holonomy, and then you can reattach using this diffeomorphism. Okay, and then so this is what's called the bending, and so this is a process of bending, and another way to do it is with using these diagonalizable ones. So these are all going to be lens because we will be able to use some bending result. I mean the stability results for small t's and so on. Okay. Okay. So